page 97, they are talking about this experiment, which we are not doing in class, but we're going to just kind of talk about what the experiment is. As you can see, they built this thing with a paperclip cup that's held up by a paper clip attached to a rubber band. And what they did is they put little weights, little washers that are basically like little weights, in the paper cup one at a time. And then they measured to see how far the rubber band stretched out each time they added a weight. So now let's look at the next page on page 98. Skip down to the middle of the page. It says a group of students performed a similar experiment with a spring and various masses. The data they collected is shown in the table below. So they're saying when they put in a 2-gram weight, it stretched to 6 centimeters. When they put in a 4-gram weight, it stretched to 12 centimeters, and so on. So first it wants us to make a graph of the data from this table. So as a reminder on how to graph a point, this would be 2, 6. So this first one would be 2, 6. That means you start at 0, 0. We are going to go to the right 2 and up 6. So notice the bottom is counting by 1s and the side is counting by 3s. So be careful when you are plotting these points. So go ahead and plot the rest of these points from the table onto your graph. All right, once you have these all graphed, number 9 says, how much does the spring stretch for each additional gram of mass added, and explain how you found your answer. Ahmed.
It goes by 3.
How do you know that?
Because when you find the unit rate, 1 mass, that means it's every 1 mass, it stretches by 3s.
Very good. So how much does the spring stretch for each additional gram? That would be, it stretches 3 centimeters. For each gram. And then when it says explain how you found your answer, I'm glad you used the word unit rate, because that's exactly what we were looking for here. So you can say I found the unit rate by dividing 6 centimeters by 2 grams. So 3 centimeters per 1 gram. This is how we need to get used to writing these explanations using the mathematical language like unit rate. Number 10 says to use the student's data to write an equation that gives distance d that the spring will stretch in terms of the mass m, and explain your equation. So if it's an equation, what does it need to have? An equal sign. An equation has an equal sign. So I know that I'm going to have an equal sign. I know I'm going to have 2 variables. Distance is d and mass is m. So I need to have something with d and m and an equal sign that explains the values in that table. So take a second and try to come up with an equation Maybe try to use one of the points so we know that 2 grams equals 6 centimeters. So somehow to come up with an equation. Does anyone have an equation? Okay. Here. So it should be 3m equals d, or d equals 3m. Because whatever mass you put in, so whenever you put in 2 grams of mass, you would multiply that times 3 to find out the distance. So your way, it would have been multiplying the distance by 3 to find the mass. So it's backwards. So when we put it, so think about plugging in 2 grams of mass, so 2 times 3 equals 6 centimeters of stretch. So if you explain your equation, the stretch is always 3 times the mass. Alright, so for number 11, it says to use the equation to determine the length of stretch for a mass of 1 gram, which we already talked about. So I'm going to use the equation that we just came up with, d equals 3m, and I'm looking for the distance when I have a mass of 1 gram, so where am I going to plug the 1 in at? Where? M, because it's mass, the mass of 1 gram, so I'm plugging it in for mass. So d equals 3 times 1, which is 3. So the distance would be 3 centimeters. Then use the equation to determine the length of a stretch for 7 grams. So where am I plugging in 7? M. If the mass is 7 grams, I'm plugging it in for M. So that's going to be 3 times 7, which is 21. So it stretches 21 centimeters whenever you put in 7 grams of weight. Number 13. Use the equation to find out what happens when you put in a mass of 13 grams. So where am I plugging in 13? M. So what is 3 times 13?
39.
39. So the distance would be 39 centimeters. And then, sorry, for 11, 12, and 13, we need to graph those 3 points on the graph. So what would this first point be as an ordered pair? What did we plug in? 1. And what came out? 3. What would the second ordered pair be? 7, 21. And then the third ordered pair? 1339. So let's go ahead and graph those 3 ordered pairs on the graph. Backwards on page 98. So we have 1, 3, 7, 21, and 13, 39. The previous one. All right, 14A. What do you notice about the points you graphed? Right. Okay, so they all fall into a straight line. How could you take this graph and make it represent the set of all possible masses and corresponding stretches? What would I need to do to the graph to make it represent all possible masses and corresponding stretches? Jordan? Cam?
You could drop an arrow from 0, 0 all the way up so that shows like that it keeps on going.
Good. So we need to connect all of the dots with an arrow on the end to show that it keeps going. Do I need an arrow on both ends?
No,
Why not?
because you can't have a negative distance.
You cannot have negative distance and you cannot have negative mass. So it stops at 0. I do not want to draw an arrow back this way. So the only direction you want to draw an arrow in is going up. So for part B, connect the dots. And draw an arrow on the top end. What is the y-intercept of the graph? So where does it cross the y-axis?
0,
At 0, 0. And what does that represent in this situation?
When you put 0 mass, it stretches 0.
Right. So when there is no mass, it does not stretch. And it asks for the reasonable domain. So that is the inputs that you can use that make sense in this situation. So what is the reasonable domain? What can it not be?
0.
Negative.
It cannot be negative. Because you cannot have a negative mass. So how can I write all positive numbers as an inequality? Jordan. Greater than or equal to. So we're going to say m or x, whichever one you want to use because m was the mass, is greater than or equal to 0. And then it says explain why, because mass can't be negative. All right, on the next page. Now Mr. Hardo's class conducts this experiment with a spring and a set of weights. And they record the data, but some of the information is missing. So number 17 says, how much does the spring stretch for each additional ounce of weight? So go ahead and figure out how much does it stretch for each ounce of weight. Your group. How did you figure that out? Good. So how much does it stretch? That was 2.5 inches per ounce of weight. And how would you do that? He said he divided 12.5 by 5. So you could have picked any of the 3 that are completely filled out and divided. And that was you finding the what? The unit rate. So we found the unit rate. Find the unit rate by dividing the inches by ounces. And now that you know that information, oh, sorry, I did not answer that correctly. We need to write an equation. So what would our equation be? So again, we can call this the stretch, can be the distance is what we called it in the previous one. And then the weight can be W for weight. So how do these two things, how do you get from one to the other, Sean?
W equals 2.5 times.
Megan?
D equals W, 2.5 W.
Good. D equals 2.5 W.
D. What?
Again, you are multiplying 2.5 times the weight times the W to find out what the distance is.
So it would be 2.5 W.
2.5 W.
She said D.
D equals
D equals
2.5 W. Yes.
That is exactly right.
Okay, use this equation to complete the table. So go ahead and use this information in the equation that we just figured out and complete these last three lines. So what are you doing to each of these ounces, each of these weights? Multiply each one by 2.5. So, when you plug in 12, what do you get?
30.
30.
What do you get when you plug in 15?
37.5.
And when you plug in 16?
48.
40.
48.
40. My bad.
40.
I just
Alright, check your understanding. Quickly do number 20 on your own.
Yes.
So how much does the spring stretch for each additional pound of weight?
4.
4. How do you figure that out?
Find the unit rate.
18 by 4.5.
Find the unit rate by dividing 18 by 4.5. Alright, moving on to the next page. The Empire State Building in New York City is 1,454 feet tall. How long do you think it will take a penny dropped from the top of the Empire State Building to hit the ground? Just go ahead and write down an estimate on your paper.
2 years. I remember seeing a video about it, but I forgot. It was like 3 months.
Okay, so in 1589, the mathematician and scientist Galileo conducted an experiment to answer a question much like the one you just answered. He dropped balls from the top of the Leaning Tower of Pisa in Italy and determined the time it took them to reach the ground. He used several balls identical in shape but in different mass. Because the balls all reached the ground in the same amount of time, he developed a theory that all objects fall at the same rate. His findings can be represented with this equation: h of t equals 1600 minus 16 times t squared, where h of t represents the height in feet of an object t seconds after it has been dropped from the height of 1600 feet. So if he stood at the top of the Leaning Tower of Pisa, it was 1600 feet above the ground. and he dropped all of these different balls, and they all fell at the same, they all hit the ground at the same time. And so he came up with this equation. So we are going to plug in these different amounts of seconds to find out the height. So at 0 seconds, let's plug it in. We're plugging it into this equation, 1600 minus 16 times 0 squared. So that would be 1600 minus, what is 0 squared?
0.
Times 16.
0.
So 1600 minus 0 is
1600.
1600. So at 0 seconds, the object was still at 1600 feet, which makes sense. That means he hasn't dropped it yet. 0 seconds in, it's still going to be right where you started. I want y'all to go ahead and work out this table. So you are plugging in each value of seconds in for t and finding. Go ahead and check your answers on the board. So notice he started at 0 seconds, 1600 feet above the ground. Then at 1 second, it was 1,584 feet above the ground. What seems to be happening as you go down? It's going down. What happens here? It hits the ground. Okay, so let's go ahead on the next page, and I'm going to leave this here so you can see it. But on the next page, it wants you to graph these on the graph on number 4. So graph these on the graph on number 4. I'm going to leave it up so that you can see what it looks like. You should have a graph that looks something like this. Now, we need to think about, do we need to connect these points? Is there time between like 0 and 1 seconds, between 1 and 2? Yes. So, yes, I need to connect these points because it's not just like 1 second, 2 seconds. There's a lot of time in between those. So we need to go ahead and connect these points, and no, it is not a straight line.
Yeah.
And that's okay. It's still continuous because the points are still connected. It's not just separate points. But it is going to be sort of a curve instead of the a straight line. Let's go back to number 3 real quick. It said, why would negative domain values not be appropriate? What is domain in this situation? Time. So why can the domain values not be negative? Right, time is not negative. Number 5, it wants to know what is the reasonable domain and the reasonable range. So for this function, in this situation, the domain, what is the smallest domain value? 0. What is the largest domain value? 10. So write it as that compound inequality. 0 is less than or equal to x, which is less than or equal to 10. And then we need to do the same thing with the range. What is the smallest range value? 0. And what is the highest range value? 1600. So 0 is less than or equal to y, which is less than or equal to 1600. What is the y-intercept? Where does it cross the y-axis?
Oh no, 0, 15, or 1600.
Good. 0, 1600. It crosses the y-axis up here at 0, 1600. And what does that represent? What? Jordan. Okay, so it's the what point? It's the starting point. So the object starts at 1600 feet above the ground. And then number 8 says, what is the x-intercept, which we haven't talked about, but kind of using the context of this, what do you think that means?
What hits the x?
Where it crosses the x-axis. So where does it cross the x-axis?
10.
10.
At 10, 0. So it crosses at 10, 0, and what does that mean? That's where it hits the ground. This is where the object hits the ground. All right. On the next page, it's asking you to fill out your own values for the table and then graph it. So it's giving, anytime it gives you a function like x squared minus 2x, you can pick whichever x's you want to plug in to find what the y's are and then be able to graph it. I'm going to give you some easy ones. I'm going to do from -2, -1, 0, 1, 2, 3. But you can pick whatever numbers make you happy and plug them in and solve for x.